tutorials, if I am not completely dead by then, because my head is thumping right now as if it wants to do something else. Okay. We started here yesterday and we started talking about, we are trying to, the first part of the lecture will not necessarily be on temperature sensor, but let's start off thinking of them as infrared sensors. So we have done visible light from ultraviolet to partly red, and anything beyond visible is, and below microwave counts as part of infrared. Because it's a very broad spectrum, I mean, look at this way, 380 to 780 is roughly visible, that's 400 nanometers, right? And then you go for 780 nanometer to 1 millimeter. How big that range is? It's almost a millimeter range, because after nano you get micrometer. So 1000 nanometer will be roughly 1 micrometer, and then you go 1000 times more, you get a millimeter. So it's a very broad range of intensities which we are looking at in infrared measurement. So we often divide it into a couple of few, 3 or more, there are many sub units of there. So we started talking and said visible light covers the various colors which you can see. Near infrared is a response coming out of very hot objects. We are looking at 780 nanometer to 3 micrometer here. A thing to see is also the photon energy. Some of you who were not there in the first day, we calculated the photon energy of visible light photons. How do you calculate photon energy? What's the formula? Hc by lambda or h nu, where nu is the frequency. So it's Planck's constant multiplied by the frequency of the radiation, or Planck's constant time the speed of light divided by the wavelength of radiation. The reason why it's important will become apparent very quickly. We did this earlier, but I will do a revision just to remind us where we are. As you go further higher in frequencies, this is where we are looking at room temperature or normal heat, 300 degrees Celsius, or even higher in bodies at room temperature. So something like I and you will be having a photon energy of the ballpark of around 0.05, 0.1 electron volt, and mostly radiations in the terms of tens of micrometer of wavelength. Of course, there are things even before that. So you will see these words more frequently: near infrared, mid infrared, and far infrared. And then also see ultra far infrared, how far it is from visible ranges. Do not forget, the further we go, the photon wavelength increases, but its energy starts going down. Okay. Application wise, we have got a large number of application of infrared sensors. We can do contactless temperature measurement, and once you can do temperature measurement, there are many things you can know about a material. Generally, such measurements are not affected by visible drawbacks, things like darkness, fog, and sometimes even small objects falling in between there. So for example, our clothes, IR radiation can generally pass through that. The other big application of IR is an IR spectroscopy. When we are trying to figure out what material we have, a number of materials or atoms of this material absorb certain wavelength in infrared. So if you look at which wavelength is being absorbed, you can then say what material we have. A carbon dioxide is a very good example of how it can be measured by looking at its absorption spectrum. And then of course, but if we have temperature profile of something, we can, and that something is moving, we can identify just looking at the temperature measurement rather than having to look at this visual picture. Okay. Particularly if you have night vision cameras and you are trying to figure out if there is a human person moving or not, they are mostly looking at infrared domain. But as you can see, it depends upon what you are trying to measure. If you are trying to measure human beings, we should be making a sensor in far infrared domain. Okay. Then of course, the question is, what do you measure? Now, there are two things here. One is, okay sir, one is you measure heat, the other is you measure a wavelength. Heat is generally broad spectrum, and the way you measure heat is, your transducers will convert heat either directly to a voltage or to something intermediate. That something intermediate could be temperature, could be pressure, could be strain, could be stress. And a very good example, if it converts to temperature, then we can measure that temperature through indirect means, okay, through other sensors. Now, generally heat measurement is wavelength independent. You are not measuring a particular wavelength, you are measuring how much energy it has, overall energy it has. Now, here is a problem of heat measurement. It also heats my sensor. Right? Ideal sensor should measure heat, but should not be affected by it. That is not going to happen. Right? So, quite often in many of the other sensors like wavelength dependent sensors, we try to reduce the temperature or cool the sensor to record the infrared. To some extent it also helps in, because you know, at room temperature, at any temperature, we already have thermally generated charge carriers as well. In any semiconductor, heat itself leads to electron hole pair formation. Ideally, we would want to measure electron holes which are just being produced by my radiation, not by my heat. So heat produced, ambient heat produced electron hole pairs, they are like noise to me, or my leakage current. Even in photodiodes, in pixels, heat produces electron hole pairs. So one solution to that is to cool the sensor. Now, this is particularly when you are trying to record very low amount of intensities. A very good example is when we are looking at light coming from stars. Now, some of the stars we can see by our naked eye. A number of others we use telescopes of different type. The amount of light coming from these stars is very, very low. So, quite often we are looking at few photons, a few hundredths of photons. If our sensor itself is producing 100 electrons as part of thermal noise, I will not be able to read these 100 photons. So, 100 photons will produce 100 electrons. My sensor noise is, say, not even 100, it is 50. Then my noise to signal to noise ratio is quite low. So, quite often in these extreme applications, we cool the camera and cool it to very low temperatures, sometime at 4K, sometime at around 70 or 80K. And at that temperature, we believe that, well, the thermally generated charge carriers will be low, which means whatever we will be measuring will be intensity effects. However, for heat based sensor, that does not do much good. Cooling does not help. Cooling helps with sensors measuring infrared radiation. The other drawback of heat based sensors, they are not very good in frequency domain. They can only measure up to 100 hertz. You need the heat to affect my sensor. You need it to have a temperature change. And as you know, temperature change generally takes time. Right? Most material have got an inherent ability to try not to heat. And typically the relationship is of the order of T to the power alpha, alpha depending varying from sensor to sensor. The other alternative is we measure, think of heat as photons. It is an electromagnetic radiation. We talked about heat covers everything from visible all the way till a millimeter of radiation. And then the design becomes very much like you design a camera. So, towards the end of it, we will do a camera design with heat measurement things. Okay. Of course, you have to choose a suitable material, and we will see very soon how. Now, it is wavelength dependent. It is not going to measure heat. It is going to measure that particular wavelength which we are interested in measuring. Now, here cooling improves the spectral sensitivity of the material. Now, and also these sensors can be made to be at very high frequency of operation. You can also go up to gigahertz of frequency. So, if you remember, this is the effect which gave Albert Einstein his Nobel Prize, right? Though we remember him for his theories of relativity, the special and general theory, it was the photoelectric effect which got him the Nobel Prize. So, if you remember from your high school days, and photon with sufficient energy hits a substance, it passes the energy onto it. If my energy is high enough that the electron could move, then I get a photoelectric current. Another theoretical foundation there, you had remember concepts of band gap. Has it been taught to second year students? Right. So, you recall things saying that insulators, so there are bands of energy where we know electrons are there. There are bands of energy, if they have this energy, they will start moving. So, the valence band, which I am there, conduction band is when they will move. So, for insulators, that band is quite big. So, you need to give a lot of energy for electrons to move and to conduct electricity. For semiconductors, this band is moderate. For metals, these bands overlap. So, electron is always available to carry conduct. Now, the moment you apply a potential difference, the electron is happy to move. For semiconductors, it is in between. Now, this band gap comes into play very interesting. So, the photon should have enough energy to overcome this band gap. So, now band gap of silicon is 1 point, well, what is the band gap of silicon? Sorry, let us do the reverse calculation. Here I have done the forward calculation. So, if we take the band gap of silicon, let us try to calculate what is the highest photon it will be able to measure. Okay. So, what is the band gap of silicon? If you do not know, do a Google search. It is perfectly fine to find resources from it, and all of you guys are carrying mobile phones anyway. Can somebody give me the band gap of silicon? You have your mobile phones? 1.12 electron volt, right? So, that is the energy I have. So, that is the band gap I need to overcome. Now, the question is, what is the highest wavelength I can measure with 1.12 electron volt, right? So, you have 1.12 electron volt on one side and you have hc by lambda on the other side. Let us try to find what will be the lambda. So, hc by 1.12 electron volt, and somebody can do that calculation. You have your phone, so you can even ask Google to do that calculation. That is perfectly fine for me. Now, will Google do it? If you just enter hc by 1.1 electron lambda, does it do that? How much is that? Throw a number, worst case it will be wrong. You can see all the eyes are looking down. The moment you look up, you see eye to B, so you have to give an answer. Actually, you know what? While you are doing that, I will also do it, and let us see how hard can it be. 1100 watt units, nanometer. So 1.1 micrometer. Actually, while you guys were doing this calculation, I found a web page which does photon energy calculation. Did you find that as well? And you just enter the energy and it gives you the photon. Were you able to find that? Okay, good. So that was till 1.1 microns my silicon could do. But actually, in the early stages, its sensitivity is not very high. The sensitivity goes from 0 onwards. For some reason, some of the reasons are these. Not every photon gives birth to electron-hole pair, because we have something called photon detection probability. Some photons will just pass through. Right? It's not that immediately the first photon material it hits, it gives birth to the electron-hole pair. There's something called penetration depth. That is the depth on the structure. So photons are coming with an energy, right? So they try to penetrate the material. So at some penetration depth, do they pass on their energy to them? So because infrared photons have got decent energy, they try to go deeper. So their penetration depth is higher than, say, ultraviolet photons. So if you make a structure which is very, very thin, even though its band gap will be fine, the photons will pass through, or a large number of photons will pass through. Now let's ask the other way question. Now somebody of you will have the Omni calculator on your phone anyway, right, which finds this thing. So our near infrared goes from about 780 to 3 micrometers. Okay, we said silicon will work till 1.1 micrometer. After that, it doesn't work. If we want to find 3 micrometer, what material should we use? Okay, it's the inverse question now. In order to do that, the first thing we need to do is to find the photon energy there. So 3 micrometer, what's my photon energy? 0.4 electron volt, and you can do the same calculation again. So I'm not going to bother you with calculations. Okay. Now let's try to find a material. So let's do a Google search again, because rather than throwing a material chart, so let's look at or just do a search for band gap of typical materials, typical semiconductor materials, and see if you find a semiconductor material whose band gap is small. Now we need a small band gap material for these things. Okay. So you should be able to find a table somewhere which lists band gap of typical materials or typical semiconductors. Did you find something? Lead sulfide. Okay. What's the band gap of something like indium nitride? Or indium arsenide? How much is indium arsenide? Tell me the number. 0.36 electron volt. Now the other thing which some of you might have known, that in So silicon is a group 4 material, if you remember your periodic table, right? So what else do we have in group 4 other than silicon? We have carbon, we have germanium. So germanium exists as a semiconductor, carbon exists as a semiconductor in a very fancy fashion. It's a very interesting material. It can be a conductor, semiconductor and insulator all at the same time depending upon how you build it. Little wonder we all are made of carbon, right? The other way to make semiconductors is to take one material from group 3, another material from group 5. You also have two 6 semiconductors, one from 2, one from 6. Now most of the tables which you would have seen would be typical materials. Now people also do something called band gap engineering by introducing sufficient dopants to try to change the band gap of the material. So suppose you try to merge aluminium in it, okay? But these indium based sensors can act on these devices. Can we go even higher? Can we go till mid infrared? So you have got a table on your phone, mid infrared goes till about 0.21 electron volt. Can we use such materials for that kind of sensors? Is there any material which can do that? Now that would be lead based, which is found anything which can go to that level? I will also do search for you. Now generally I can give you these in a table, and what I have found, the moment I put a table, people's brain go to sleep. That's why I make you search, do something. Have you guys covered direct band gap and indirect band gap in your semiconductor physics till now, or not yet? Okay, if not yet, we'll stick to standard materials. Lead based materials can act as a large infrared sensors. So now you can see the problem here. The more is the wavelength, is difficult to find simple materials. Why the band gap is there, we can discuss this in a later lesson. But for the time being, at least in near infrared, we have got a lot of material which we can use. In your table, you would have seen a large number of material which have got this band gap in this 1.59 to 0.4 electron volt regions. And people often divide this near infrared also in different bands. It's not just one big band. So you'll have sensors around 1 micrometer, 2 micrometer, and so on and so forth. Okay? So let's start looking at the type of devices which are made here and what are the things which is required. Now yesterday we talked about resolution. Now for these sensors there are two things which are of interest to us. One is the temperature resolution. If my temperature is changing by X, what's my signal changing? That's fair enough. The other is spatial resolution. Remember, when we take cameras, we put large number of pixels and we call it resolution because this then determines what's the smallest distance in space I am taking a picture of. Right? More pixels, the area, I'm taking the same picture with more pixels, which means each space is denoted by higher spatial resolution. Now historically, IR cameras have lagged significantly behind visible cameras on their spatial resolution. Say you can get a 100 megapixel visible camera, but 100 megapixel IR camera is very difficult. Even few megapixel IR cameras are difficult to get. Unless of course you are a military contractor and you are making just one IR camera for one particular thing and you can charge a couple of million euros for it. Okay? So spatially speaking, IR cameras are still lagging behind their visible counterparts. By the way, can somebody figure out what's cadmium-based materials band gap? Cadmium, indium telluride for that matter? That's another nice material to use for IR sensors, but anyway. Okay. Now, the way we design IR sensors is, so you know, in case of visible sensors, we have kind of standardized our design now. It's silicon based, few transistor pixel circuit, and we have made a fairly standard approach of designing them. In infrared, that has not been the case. It has also not been the case because there are different ways of measuring infrared, and there are large number of physics based things which happen here. So there is Seebeck effect, which essentially says if we have some materials which are at two different temperature and you connect a wire between them, you will see electrons will flow as an effect of the difference in temperature. Okay. There is pyroelectric effect, which says that if my temperature changes, that leads to a voltage in some materials, not all the materials for that matter. And there are parametric sensors which somehow manage to change voltage or current based on temperature based effects. These could be changing resistance based on temperature. Now, we know most resistances are temperature dependent. Such sensors are called bolometers. They could be changing pressure. Such sensors are Golay cells. They could stretch a material, and there are many such. And even something as simple as the forward bias voltage of diode. Remember, you have done quite a lot of diode equations and transistor equations. Temperature always appears one way or other. If nothing else, Kt, where K is the Boltzmann constant and T is the temperature, appears at many locations. So wherever it appears, you know whatever my output of semiconductor material is going to be, it's going to be temperature dependent. So I can use that as a temperature sensor. So if nothing else, you take a diode, just design a simple diode, measure its current, that is a temperature sensor, if we can dissolve it into very small amounts. Does anyone remember the diode equation? How is it related to temperature? So the forward bias current is Is e to the power Kt something. That's what I said 5 minutes ago. You guys should be better than me, right? I did these courses 25 years ago. It's the I naught term which appears there. That is the heavily temperature dependent. Okay, so I naught times e to the power volt is something. There's that. Actually, we will see it's not a very easy relationship with temperature. As a rough rule of thumb, we say for every 10 degrees Celsius it doubles. So it's an exponential kind of change, but that's a rough rule of thumb. It also depends upon what type of diode you have, what material you have made. Okay. So some of you might have seen things like this in mechanical engineering lectures, wherein we may use the Seebeck effect. Essentially, we use two different material and put one material in hot, one material in a cold place, and the other material is looking at your at your heat, and then most material will have some Seebeck coefficient. Here you have got alpha A. There was a pointer here which has disappeared. I can't move my mouse here. So alpha A minus alpha B, whatever is the temperature difference between these two materials will lead to a voltage being induced in the output line. Okay. Now generally the voltage produced by just one thermopile is quite small. So whenever you have one sensor producing a small response, there are 2 or 3 things which you can do. You can either put an amplifier after that, or you can try to increase the amount of response by putting sensors in series. So one is producing a small amount of volt. If I have n number of these, then I will get n times that voltage. Okay. So quite often we make series of these, particularly when we are making in chips. Now these sensors have been used for last 50 years, or if not 100 years. They are nothing new. What we are going to discuss is how do we put it on top of a silicon chip. So, to do that, I mean, here are some examples of doing that. This is a micro electromechanical sensor chip, wherein you can see they have got a hot junction and a cold junction, and they are trying to keep these structures away from one another. And if you look at the literature, there are tons of such papers. Okay. Here is another example of this, wherein you have encapsulated your cold structure in a structure, and then you have made a 3D structure on top of that. I gave you these examples just to show in the micro electromechanical system world, people where they are trying to make smaller mechanical structures, and they have freedom of the kind of structure they do. There has been a large number of such sensors which have been built. But before that, let us try to figure out, so here we need two different type of material, right. One which has, and ideally it would be good because the voltage produced is the difference of their Seebeck coefficient times temperature. So, ideally what we should make is these two materials having large differences of their Seebeck potential. Then I will get high voltage, and my apologies, now I am going to bore you with a table. So, here are some materials which we have available in the CMOS process itself. I am making out of silicon, I have got polysilicon, I have got silicon on insulator SOI, and then I can dope them with N type or P type. Okay. So, doping then changes my Seebeck coefficient. So, from here, I mean, you can see things like silicon on insulator has got fairly high Seebeck coefficient, but it's a bit negative. Polysilicon seems to be fairly good there, right? It's 190 units volt per microvolt per Kelvin. And it's available. We made using polysilicon, we made the transistor. So, I don't need to introduce a new material in my process. So, other things like bismuth telluride which are on top, they are not inherently available in a silicon process. Right? Even silicon on insulator means I have got an insulator base, then a dielectric, and then silicon. It's a costly process to make. So, people used to make chips on things like silicon on sapphire or silicon on diamond, but polysilicon itself is available. So, I already have one material. Now, I need a second material. So, one I selected 190, the other would be good, either it has got 1000 or 1, right. Then I have got a good range, isn't it. So, here is the characteristic of some other materials here, and you can very well immediately see that metals, or at least some of the metals like aluminum or gold, have got very low Seebeck coefficient. So, if I already choose polysilicon with around 190, or if I can dope it nicely, I can also get slightly higher. The beauty of some of these metal is aluminum or gold is tricky to introduce in a CMOS foundry, because gold ions start diffusing in silicon and start changing the transistor properties. But yesterday when we were doing, at least those who were doing layout, they saw we had metals, metal 1, metal 2, metal 3. In most larger processes, we used to use aluminum as a metal to connect transistors. This is very interesting because I already have polysilicon and I have aluminum, which means I can make such sensors on a classic silicon chip without introducing any other material. The whole crux of my course is what can we do on a silicon chip. You can have fancy materials and we can add loads of these things. But if we take one beam of aluminum, other of polysilicon, we have got a thermopile kind sensor design. And there are a number of such commercial sensors in the market. So, you can go and have a look at these and you will find some things, a lot of these are there in the market there. The problem of these is twofold. One, you need to cool a junction or keep a junction cool. Right? So, you need to shield it somehow from incoming heat. Classic sensors, in diode sensors, all the diodes were open. they are just receiving light. If my cold junction also gets hot, that will be not nice. So, quite often such sensors are made with one sensor on a chip. You are essentially looking at just the amount of heat. You are not looking at a particular radiation. You are not trying to take a heat map. You are trying to measure heat overall in the room. The other thing which is often designed is pyroelectric based sensors, and then you have got another property to look at for pyroelectricity. Okay. Here if you look at things like aluminum nitride, do we have aluminum nitride here? We do not, but you have got pyroelectric coefficients, if you look at the last column, of quite a lot of ceramics. Now, where do we use ceramics in silicon processes? So, till now we did not talk about how you package a chip. A chip comes packaged, and this is where we will be using quite a lot of other things. Now, people have tried making pyroelectric sensors from aluminum nitride, because again aluminum was available in silicon process, but it has not been a fairly good success because aluminum nitride itself has a very low pyroelectric effect. Doping it something with scandium, making it a scandium aluminum nitride, that has been a fairly decent success, and people have tried making structures like this for, you have got a titanium, different electrodes, you have a sensing layer in between. So, trying to make a pyroelectric sensors on those kinds. The sensor which I believe has the most prominent use will be bolometers, and that is the one which I will be covering in a bit detail. So, the word bolometer comes from bole, which is Greek for beam of light, and these sensors work in a much simpler fashion. Essentially, their temperature their resistance changes with temperature, okay? And we have a temperature change coefficient which is 1 over RB delta RB time delta Ts. So, how much does my temperature change at a given, how much does my resistance change at a given resistance as my temperature changes? Now, this temperature coefficient of resistance for metals is positive, which means more temperature change, more does my resistance change. For semiconductors, I have written it negative. It is not purely negative, but in most room temperature it is kind of negative. Why would you think the resistance of a semiconductor will reduce as I increase my temperature? Sorry? So, why is that not happening in metal? Metals also you have electrons which can move freely, right? So, one argument, yes, is high the temperature, more energy electrons have, they can move faster. But then metal resistance should also fall down. But we know standard resistors, their resistance increases with temperature. So, the bottom line there is the more temperature you have, the more thermally generated electron hole pairs are being generated. In semiconductors, you have got larger number of charge carriers available to carry current. If more charge carriers come in, your native resistance falls down. Good. Now, look at the temperature coefficient of resistance for various metals and various semiconductors we have. Metals like aluminum and copper we have in the process, and they have very similar temperature coefficient of resistance. So, percentage change in temperature is fairly smallish. For semiconductors, we have got bigger changes here. Okay? And some semiconductors, something like gallium arsenide, they have got very good number compared to metal. Okay? Now, gallium arsenide is used for making a large number, not larger, but decent number of electronics, particularly high speed electronics. We use 3-5 semiconductors, though their use is reducing with time, but they are still there. Now for some maths. We have done this lecture till now without maths, so some of you might be feeling a bit bored, right? So we are now going to look at heat conduction equation. We have one mechanical engineering in house. You can explain this better than I can, right? You guys should have done thermo heat flow. And he's saying, nah, don't remind me of the bad days of looking at laws of thermodynamics, the 3 laws which still taught, isn't it? You guys were taught laws of thermodynamics. Sorry? So you have forgotten it by the time you start MTech. So the classic heat conduction equation is the one equation on top. There are few things to look at here. C is the heat capacity. Essentially it is saying how much radiation is being converted to heat. Not all of that will be converted into heat. Okay? Next is thermal conductance. That is basically saying, so I have got a sensor and I have got my environment. What is the resistance between environment and me? It could be environment or it could be a heat sink, somewhere where heat is going. And last is of course the absorbed radiation power, and that is with an exponential attached to it. Now this is a simple differential equation. It's the first order differential equation, right? So all of you should be able to solve this. I'm not going to bore you with solving this. You will get a relationship something like this. A delta T would become a function of incidence radiation, the conductance, and a time constant here. The time constant would be a fraction of your heat capacity and thermal conductance. Remember we did lumped mass models where we looked at thermal effects as well. So I'll be talking in terms of electrical properties here. As temperature of the so temperature of the sensor will rise with a rate of P incident by C. So you see we have from this relationship you can come up with that. The limiting value would be a steady state value where actually plus some whatever is the incident radiation divided by my heat conductance. So I'll reach a steady state value in due course of time, and you might have seen as we start heating we will reach at one point of time. Typically if you have long cylindrical devices like wires, that is the kind of heat conductivity equation you have, which looks very similar to the resistive conductivity. So what's the resistance of a cylindrical wire? Rho A by L. Sorry? So area of, so rho L by A, right? So L being the length of the conductor, area being the area of cross section. If you look at the conductivity, it will be 1 over R A by L. Electrical conductivity. So the thermal conductivity has a similar formulation as the electrical conductivity. And of course we define a constant here which then tells us how it proceeds. Now from there we could calculate the responsivity of the sensor, because we wanted to find what's that what's the temperature coefficient of resistance, and that comes out to be a fairly simple number where you have got G which is in the denominator. Now there is something else which one should remember when we have got a sensor whose temperature, whose resistance is changing with temperature. Now generally we measure electrical sensors by passing a current through them. So if my resistance is increasing, what is increasing? My voltage demand. Okay? Agreed? So we said metal based sensors, their resistance increases with temperature, which in turn means my voltage demand is increasing. Now if it increases to a very high value, I will need a very high voltage, or I will be having very high amount of power dissipation. So this leads to a pole in the equation, Now, I am not going to do the equation for you, but think of it this way. If I pass the same current through the sensor, I have fixed my current, my resistance is constantly increasing, which means I am dissipating more and more power. So, at some point there is a risk I might burn out my device, I will be dissipating more heat. Now, semiconductor sensors, that is where they come nice, because their resistance is decreasing with temperature. So, I do not have to worry about this burnout effect, or there will be too much heat which will be moving this thing. So, that is the relationship. So, 2 is the waveform which shows what happens to the voltage, what happens to metal based sensors, and then this is voltage by current. So, we are plotting the resistance here, okay, versus what happens to your semiconductor based sensors. So, you can see the power dissipation or the burnout effect in semiconductor based bolometers would be better than pure metal based bolometers. And that has been the trend as well. We are seeing more and more. Now, this is a very good trend. It plotted things like how are resistance based sensors working compared to diode based sensors. That is one. So, as said right in the beginning, you can use a simple diode's current also as a temperature sensor. So, if you just look at various sensors which have been proposed versus their pixel size. Now, why would we want to reduce the pixel size of sensors? Smaller is the size of the sensor, large number of sensors I can put on a chip. Now, bolometers are interesting because essentially you can do an array of bolometers. So, you can take an image. Little wonder diode based sensors, their size is reducing because you can make transistor processes in smaller and smaller geometry. But the other thing worth checking is, what was the size of the diode sensor which we took in while designing camera pixel? 3 micrometer by 3 micrometer. These are still significantly bigger than our camera pixel. We are looking at 20 micron, 60 micron or that kind of sizes. So, while we can make an array, the individual pixel is still comparatively larger, which means the number of pixels which we will have is still fairly small. Now, earlier this is how we were making our bolometers. Typically, you will have a metal absorber, my brain is dead today. And then you could design, if you are designing of amorphous silicon is, remember we looked at the temperature coefficient of resistance, silicon was fairly good, and we designed something like a 100 nanometer thick structure which is sandwiched between 2 dielectrics. So, if you look in this structure, you have metal absorber on top, silicon dioxide are dielectrics, and in between we have amorphous silicon which is a semiconductor which is acting as a sensor. Or people were using some sort of vanadium oxide together with silicon nitride. Okay? And this is how you will be typically be making an IR absorber. So, if you are making, say, here is an aluminum based thermistor, you will create long arrays of it, because you want as big an area as possible. The more the area it has, the more heat it will absorb. So, and making these fingered structures help you increase the area of the structure. And this also gives you longer length while keeping area of cross section small. A typical diode based bolometer would be something like this. You can see there is a PN junction there, and then you have an absorber layer, a heat absorber layer which is to typically be made of metal. A number of these are not made in classic silicon processes. We use silicon on insulator processes. We want a good thermal material below which is not getting itself heated. We would want the sensor to be heated, not the package and not the substrate on which it is. Good. Then is the question of, so that was a sensor material which is less of an interest to us. We know we have material. How do we read it out of this? So, we know a voltage is changing or current is changing because the Temperature is changing the resistance, which in turn will change my voltage or current. If I apply a fixed voltage, current will change. If I apply a fixed current, my voltage will change. So what kind of circuitry we have applied? So direct injection circuits are very similar to pixel circuits. So we designed a pixel circuit in the lab yesterday, right? We had a diode, few transistors. For bolometers, you can kind of design the same circuit. Right? You take the current produced by bolometer, integrate it on an external capacitor. Now, in case of image sensors, we are using diode as something which was measuring the current. Diode itself has a capacitance. So we are integrating that current on the diode capacitance. If we are using a bolometer based on another material, not a diode based ones, then you have to build an external capacitor to integrate that charge on it. Such devices can be made. They have been seen to have poor linearity and they are a bit noisy. A better solution could be not to measure. They are a bit noisy because now the capacitance which you have is coming in parallel with my bolometer. So whatever I am integrating is also affecting the bolometer operation. So one operation could be to buffer my sensor from rest of my electronics. And because it's a current based sensor, we can put a current mirror which hides the rest of the electronics with my sensor. I was going to cover the last topic, which is capacitive transimpedance amplifier. They work even better with bolometers. Basically, you are converting a capacitance into a voltage output. So this is an op-amp based circuit which you can build. Now you can immediately see why some of the reasons why our pixel is not becoming smaller. All these circuits consume a large number of transistors. So if you're making a transimpedance amplifier, that will be about 20 or 25 transistors. So you have 25 transistors, an array of 25 transistors, which inherent area will be bigger. So despite the fact bolometers can be made very nice and can be made smaller compared to others, the individual size is still struggling. We had a project in Glasgow where we tried to make a visible camera and infrared camera below that. So the idea being infrared has got energy which will pass through visible completely. So we make a camera below that so that it passes through the visible part. And we thought we can take the image and we can take the visible image as well as the infrared image at the same time. Two problems happened. One was we could make the visible pixel very, very small. So I'm taking the scene with say 1 megapixel, but I only have 10,000 infrared pixel. So how do I correlate the infrared part with the visible part? I mean, think of it this way. You take my picture, okay? A normal camera will tell you, the picture taken will be easy to identify where my nose is, where my ears are, where my eyes are. Because I have got tiny pixels or the retina in my, not the retina, but you can see the eyebrows and the other things. But if your infrared pixel has got less resolution, maybe my whole eye is coming out to be 1 pixel. So finding boundaries becomes very tricky. How do we correlate these two? The other thing is the optical assembly. How do you make lenses for these, something which covers the whole broad spectrum? So as a sensor wise it works, but broadly speaking as a system wise we had difficulty. So right now most people will try to put two different sensors and try to take an image if you want to merge infrared and visible image together. It has been an active area of research because if you just look at a human being, I have an infrared profile and I have a visible profile. Right? So these two could give me some more information. If you go further high, if you look at terahertz sensors, then you can look at things which are just hidden below my skin or below my cloth. Some of these sensors are already there in the market. So if you go to some of the airports, you have these sensors which take a picture of you and then try to identify if you have got concealed things in your trouser, if you have concealed metal in your trouser, if you are carrying a gun or something. Okay? They haven't reached very deep internal objects. We are also people are also looking at sensors which can look just below your skin to look at things like skin pigmentation to identify early signs of skin cancer. All of this comes from these sensors, whose penetration depth is different. Right, we have been talking for an hour. By now, I am sure you are tired. So, we will take a 10-minute breather and then we will come back. Okay? Sir, can we stop the video recording for the time being? And in a robotic head, it should have at least all the sensors which a human head has, right? Okay. So the human head, we said, had eyes, ears, nose, skin, right, the good senses. Now skin acts as a very good temperature sensor. It's not a great temperature sensor, let's be honest, right? It kinda has a very, okay, it does say cold, a little bit less cold, warm, very warm, but after very warm it saturates very quickly. That is warm enough. I'm sweating, that's the end of my sensitivity. Right? We also do not do infrared imaging in our brain. I mean, I did ask you the other day to do experiment by closing your eyes, and if it's hot light somewhere you will still see something. But we are not a very good infrared imager. So why are we thinking of infrared or temperature sensor when trying to make a robotic head? The answer to that question would be, do we want a robotic head to be exactly the same as a human head, or do you want it to do a bit more than what we do? Now we know in nature there are all these things which we as human beings cannot measure. We cannot measure, say for example, carbon monoxide in this room. Well, we can measure, we faint, right? We start having headaches in carbon monoxide. I mean, I'm having a headache, I don't know due to what, but it would be some chemical imbalance in my body. So I'm measuring that system, but quite often we don't know what we are measuring. Right? The body kinda knows it's not good for me to survive. So the reason why we are thinking beyond classical sensors is to ascertain the ability for it not only to work as human, but to as a supportive to human beings. As a nose, a lot of research work has gone in making electronic nose. And I have been hearing this word electronic nose ever since I was a bachelor's, or ever since I was a school student. And we still don't have one which is formulated yet. Okay. We still do not, an electronic nose doesn't necessarily mean something which measures smell, because quite frankly smell is a kind of weak sensor. People who do research on smell will not agree to it, but think of it this way. You go to a very smelly, you have a very nice smelling flower, after a minute your nose adjusts to it and you don't feel it, right? Or if you go to a pungent room, or if you smell it for the first time, but we very soon adapt to it. Compared to everything else, that adaptation is the quickest. So, and we are not as good as, say, our other counterparts in animal world. I mean, dogs can have much better smelling abilities than we do. So this looks like it's one of those sensory things which we are losing with time. Agreed? So if I can ask my girls, students, have you tried putting flour on your hair? Does it continue to smell for the rest of the time while you are wearing it? So brain basically says, yes, it's there, I know it was good, I don't need to know anymore. Agreed? Can we just pause for a minute? Just pause for 1 minute. Okay. So electronic nose, this is where there has been a lot of work which has gone into building electronic nose, but we still are far away from that. The other thing which has happened is reproduction. With camera work, we can reproduce an image, right? But the vice versa has been a bit tricky. So our temperature sensor, which we saw in the morning, would be equivalent to our skin which we have. And skin is a very good sensor. In another way, it's a distributed temperature sensor. Okay, this is an experiment which will be worth doing. Oh no, we do that. Sometimes our legs are in cold water and we feel that. And even though the rest of the body is in hot, so we can do differential measurement as well. Okay, so it's a distributed differential sensor. So and it's an array kind sensor. It doesn't have very high sensitivity, but it does a fairly good job of telling us where we are. Now we'll be looking at a different type of temperature sensor. So till now we were recording the outside world. How is my heat? How is my other things? So kind of sensor we have looked till now is eyes, hands, weight, force, pressure, and the distributed kind of things. Now we will try to look at my inside. How hot my body is getting from inside. Okay. Particularly when we make chips, how hot they are going to be. And this becomes fairly relevant whenever because we are operating our chips at higher and higher clock frequency, which means they are producing more and more heat. Many of the chips would have got inbuilt thermal management, wherein as soon as they get beyond a certain heat, they are brought down to, they are shut down. Okay. So actually, I wanted to show you guys a video. I know videos don't come very well on the presentation, but it will be a YouTube which will show you as to what happens when we don't monitor heat properly. Maybe we'll do it at the end of this thing. So we are either measuring the ambient temperature, which we have been doing till now, how the world is around us, or we will be measuring the on the chip sensor. Now for both of these applications, now any sensor which goes on the chip, ideally it will be good if we don't bring a new material on a new type of device. It will be good if we measure something which we already have. And we said initially that diode is a fairly good temperature sensor. Now all of you guys know about diode operations, so this is the sum of the maths which I will not be doing, you will be doing on your piece of paper. So diode is what we call, it's a CTAT, in the sense that voltage is conversely proportional to absolute temperature. It's not measuring 27 degrees Celsius, but it's measuring the temperature scale in Kelvin. And this is generally of the order of 1.5 millivolt per Kelvin. So for every Kelvin, that is the temperature coefficient of diode, and it's negative. Now if diode can be used as a temperature sensor, so can the base emitter junction of a transistor be. So you have done the bipolar transistor in your courses. The base emitter junction is kinda a diode. Right? It's a PN junction or an NP junction depending on what kind of transistor you have. So that can be also used as a temperature sensor, and that will also have a negative temperature coefficient. So for those of you who had forgotten, that was the relationship between the simple diode. Okay. Now I have shown here, you are right, there should be Vt should be Kb by Q kBT, Kq by T. And we can see the drain current of the diode current would have an exponential relationship with temperature, provided that was the only relationship with temperature. The IS, the saturation current, or the I naught current, the current which flows when my voltage is same as my drift voltage, that has a fairly complex relationship with temperature. It has something like this. If you look at IS, that has got a relationship based on my number of dopants, Pn and Np. It has got based on their diffusivity, dP and dN, and it has got a relationship between the length by which an electron hole pair survives on its own, because after some time it will recombine, right. So, if I have formed a hole, it has a finite lifetime after which it will recombine. So, on average we take all of these things, we will have it there. Now, you might recall semiconductor has intrinsic concentration or intrinsic number of charge carriers, which is Ni. From there you can find number of holes and number of electrons. The intrinsic concentration Ni already has a, where is my display or the stick? There is no stick here. Okay, no worries. So, you can see here, look at the line just below, above Eg is the band gap. Your Ni has got a very funny relationship with temperature. It has got a T cube and it has got an E relationship as well. Now, Eg is your band gap. That's, well, you can assume it to be constant, right. So, as a relationship, we get an Is which becomes a fairly funnily relationship to T to the power a number which is not nice number. But we can write, if you are just thinking in terms of temperature, the second last equation could be your Is relationship. Okay. Now, think of diode. What are we measuring? If we give a fixed diode current, we like to measure the diode voltage. So, diode voltage will come from the first relationship, first equation, and Is has got a temperature dependence and the first relationship has a temperature dependence. Now, for the next couple of minutes, could you guys try to come up with a relationship between Vd and temperature? So, essentially we are fitting the Is equation in the first equation and then rearranging the equation to get a relationship between Vd and temperature. Could we give that a shot? See how it works? So, first thing first will be, if I do a logarithm on both sides, Vd will come out of exponent. Okay. So, let us try it for a few minutes and see how it goes. Now, this should be fairly simple maths. Now, some of you require an examination. Who are these people? I've been told there has to be an examination for some of you. Is anyone expecting grades from this course? No? Yes, no? Because for that we need to set an examination paper. If none of you expect a grade, then I don't have to set a paper, right? My life becomes easy. So is anyone expecting grades or credits from this course? Okay. If anyone is and is shy to talk out, any examination which I organize is generally an open book examination, so you will have all the lecture material at hand. And now 5 people would like to write that exam, right? So if some of you would have proceeded down these lines, wherein you would have, there is an e to the power q eg minus qt here, and on that term we have e to the power vd minus n phi t. If you would have expanded, you could get an equation something like this. If you look at the top expression, you would get something like this. Okay? Now that is still not a very nice relationship, is it? It has got temperature in the second term, it has got T log T in the second term, in the third term it has got T, in the fourth term it has got another log of IST by I, which is not a nice relationship. If you are going to use it as a temperature sensor, it is a fairly complex relationship. One can then think of, okay, what if I have a voltage measured as a reference temperature? So that is the voltage which is response at absolute temperature T. So if I take another voltage which we will call as, say, V of TR, this value which I have measured at a known temperature, then I can place it back in this relationship and try to get an even more complex relationship here. Okay? I can do an expansion like this. Agreed? And then of course we will do the favorite thing which we do in electronic engineering. Anything which has got a much higher complex term, we can do it. So now if we ignore some of the higher order terms and then take a ratio of how is this voltage changing with temperature, we can come with a much nicer, simpler expression of the voltage coefficient with temperature. So essentially, oh, oopsie daisy, where is my mouse? So this term will disappear if you take the derivative, because they are all constants. There is Ag and there is NKTR by Q. So TR is the reference voltage at which we have measured, everything else is constant, so that term will disappear. Here there is just a function of T, so dV by T will just be this term. Agreed? And similar, here we will get T, here we will get nothing. That will expand, but we can assume that there will be many higher order terms here. Some of those higher order terms we can ignore, my apologies. And similarly in these relations, if we do ignore higher order terms, we get a fairly nice relationship of dV by dt, provided we know a reference voltage at a reference temperature at which we have measured our voltage. And this comes out to be somewhere in between minus 1.2 to minus 2.2 millivolt per Kelvin. Now if you look at these are diode characteristic curves, you should be able to appreciate the upward going curve. If we look at these curves at different temperature, you can see, see my mouse is behaving, so I can't see my mouse on my computer, so I have to keep on turning my head. You can see various characteristic curves at different temperature profiles. Now a simple diode can be used if you are having a low forward current as a temperature sensor. It can be used, but you need to worry about avoiding self-heating. because in forward bias the current exponentially rises very, very quickly. So if it rises too quickly, it will self-heat the diode, and if it self-heats the diode, it produces more electron hole pair, which then produces further current. Now this could possibly be used to measure ranges of -100 to 250 degrees Celsius. Most chips are not designed in that temperature range. So do you know what temperature range commercial circuits are designed for? What is that range? -40 to 120. Are you designing for military? That's why he knows that temperature range. That's that military range of scales, right? Commercial chips aren't designed for that extreme. Where do we get 120 degree for our commercial systems? So we design chips only till 70 degrees Celsius. Okay. Then there is an industrial unit which goes slightly more range. The military range is bigger. Okay. So this goes to suggest that an on-chip sensor, on-chip diode type sensor, provided we are going to use it for commercial and industrial application, should be good enough for these sensory application. Now we also said you could use a BJT in making a commercial sensor, a temperature sensor. Now BJTs don't exist in a CMOS process, because we would have made a chip with just N-type diffusion in a P-type substrate. Okay. Remember the other day we saw how a chip is made in a CMOS process. But BJTs do exist as parasitic elements here. So if I can stand now, so if you can look here, if we create a P-type transistor in an N-well, I would have created an N-well, I would have deposited some P plus. But if I make a structure like this, I put a P plus here, N plus here, and P plus here in an N-well, I am not trying to make a transistor, but I am getting a parasitic transistor here. This is a horizontal parasitic transistor. If you think of this structure, there is P plus here. If I take this N-well from N plus and then take this P plus from the substrate, then I have got a vertical parasitic transistor. Agreed? So BJTs do come across as a parasitic structures in CMOS processes. Now that's good, because if I have parasitic such devices, I could use them for temperature monitoring. Now here is a fairly simple sensor which tries to monitor temperature. Now we said if we apply the same current, the voltage changes in a diode as the temperature changes. Agreed? So if you look at the left hand side of this circuit, so essentially if I fix the current flowing here, or let's fix the current flowing here by these current mirrors. So how the PMOS is, if the second years don't understand, that's perfectly fine. This voltage, I mean here the base and emitter is shorted, so it's a collector base junction. This voltage should be dependent on temperature. Now this is a current mirror circuitry wherein we have got two NMOS's current mirror below that. This also means that this voltage should be the same as this voltage reference here, right? Oh, my apologies, my brain is dead. This will then change to the currents which are flowing here, and that we then allow a current to flow through a resistor, the reference volt, that will give me a voltage which has got a negative temperature coefficient, and will give the voltage as measured across the resistor will give me a temperature sensing capabilities. My brain is dead. You can see I'm slurping. The moment I start slurping, I know I've lost my ability to teach. Should we take a lunch break, earlier lunch break, guys? Okay, and then finish it after the lesson, because I am tired now. My apologies. I was hoping I would finish the temperature sensor now. What we will do after lunch break, we will finish the temperature sensor. We will do something about a pH sensor. These two sensors will certainly finish today. Okay, and I need some rest. Okay, so my sincere apologies for this, but let's do it. Meet after at around 2 o'clock today. Let's meet at 2. Okay, thank you. Okay. I'm uploading a set of tutorial problems and a set of tutorial solutions. Okay. So it will be available online for you to download whenever you want and for you to access them as well. The network is not proving very reliable right now, so what we will do is rather than updating, so the tutorial problems are already there on the web page. No, sir. Okay. The solutions were not there. So now the solutions will be online. Okay. It's the same web page. If you have not written it, just write it down. That's where all the lecture notes are also there. I gave you a textbook, a book which you can download, which has collected chapters on other aspects. You can download it now. I will keep it running for about another month, and then I will take it out. Okay. So try to download before that time. Wait till today evening, because the solutions are taking some time to upload. As soon as they upload, you can download it. So by tomorrow morning it should be perfect. The thing is, the NIT network is not working for me, so I have to use my phone network to upload, and that's not the fastest system to upload big files. Okay. Good. With that as the background, if you have taken a note of the web page. Okay. So I know I started excuse me, temperature sensors in the morning session. I'll come back to temperature sensors towards the end of this session. The plan would be we do actually, you know what? Let me finish the temperature sensors and then we'll come back to. Doesn't make any difference. So we derived the voltage coefficient of temperature in the morning, and then we realized that we can use a transistor as well as a bipolar junction transistor as a temperature sensor. So the plan of today is we are starting at around 2:50, and I will try to finish before 4 o'clock. Okay. I am aware that today is an important day for many young people. So I will let you go in peace so that you can buy your cauliflowers or whatever you have to give gifts these days. And if you have to give a flower to your significant better, you should buy the biggest flower possible. The biggest flower market is the cauliflower, right? And it's good for health as well. You can eat it, make a salad, make a sabji. And the best part is cauliflower sticks in both North Indian cuisine as well as South Indian cuisine and European cuisine. So you can't do anything better than that. For those of you who know, who can read Hindi, on this day I will recommend you to read a very nice poem by Suryakant Tripathi Nirala, or just search Nirala. Right. So Nirala wrote a poem abusing the rose. Right. So the Nirala was a communist author, communist or socialist poet. So his whole poem is an abusive allegory from mushrooms. You know, mushrooms grow everywhere, where a rose needs so much care and protection. So the poem is from the mushrooms to the rose, right? Basically saying mushrooms are common people, everybody tramples on us, we are there, whereas rose, everyone takes care of it. So if you like Hindi, that's a very lovely poem which you can read about roses and why not to buy them. Okay, dokie. So we went with simple diodes, and then I said, okay, the diode voltage, we derived that the diode voltage here becomes a function of temperature. Okay, it's a function of absolute temperature there, and it will not be a great idea to measure it directly because of other effects. Whatever we are measuring the diode voltage, if it becomes part of rest of my electronic circuitry, the rest of my electronic circuitry could start influencing its action as well. So, a simple solution to do that is a circuit something like this, which mirrors the current. So, the top two PMOS current sources mirror the current. So, the current on two sides become the same. And if the current on two sides become the same, the Vref voltage on these two sides also become the same. Okay. So, just like your Vref voltage on this side has a negative temperature coefficient, we know it falls with as the temperature goes up, the voltage starts falling down. Voltage on the other side also does the same thing, and that is why you can take a copy of it. However, this voltage has got a fairly complex relationship with temperature. We did all the analysis and we still found a fairly complex relationship with temperature. One of the reasons why we found a fairly complex relationship with the temperature, if you go back, was that IS, the reverse bias saturation current, that has a fairly complex relationship with temperature. Right? We had T to the cube, e to the power g, and so on and so forth. Okay? So, a circuit which gets rid of this IS effect completely is to look at what if I make two of these devices. Total current would be 2 times these. Okay. If I have two such devices, each one of them giving a current in parallel, the current will get added. Agreed? So, the current will be 2 times IS e to the power blah 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 blah. Or better still, if you look in the voltage terms, I will get 2 times all of this. Okay. Now, what happens when we let's go back to this circuit. So, what happens when we subtract two numbers which are logarithmic of one another? Remember, we had these log t was appearing quite frequently. So, how do we get rid of log t from an equation? So, when two numbers we subtract log a minus log b, the result becomes log a divided by b. So, if we have one source which is n times or 2 times the previous one, another source which is just as it is, if I subtract these two, because my current is in log domain, so say my voltage was a plus log of temperature, and the other one will become 2a plus 2 log of temperature. If I subtract these two, log t will cancel out one another. It does not make sense. Follow in this circuit, ignore the circuit for the time being. So, if I have one base emitter voltage which is n times, which has got n different gates in parallel, so I will get a relationship Vt times log of n times I naught. Remember, I naught is being n times. The other will be just log of I naught time. If I take the difference of these two, then I naught will cancel out, Is will cancel out, all I will get is a Vt log of n. Now, Vt was also temperature dependent, was nQt by nKt by, it was Qt, my brain is still dead, Kt by Q, right? It was directly proportional to the temperature. So, by doing a circuit like this, where we force, and we can do it two ways. We can either say we can make the transistor have n different transistors in parallel, or I feed an n times I current in that transistor. Okay. So, current voltages similarly we can use. And then if we take the difference between the voltage in these two circuitry, the difference voltage, this difference voltage between these two, that will be absolutely proportional to temperature. It will not have those funny log of terms, it will not have those complex comparators. Okay. There are similar circuitries which are, rather than having n times the current, you can have n times the diodes sitting in parallel. So now the same current is flowing, it's a current mirror circuit, but you have n times the diodes in these two between. Okay. The other alternative which you can also do is, if you have looked at the current here, you can then mirror that current separately through a third device and then say the voltage across this resistance. Remember the first circuit which we saw when we just taken the voltage across the resistance. So we can have, okay, we have got n times device times divide there, and then we take the voltage across a resistance. So now we have got both the absolute the voltage which is proportional to the absolute temperature as well as the voltage which is doing the other way around. Good. Rather than pouring you to more complex circuit, this is just a self-starting circuitry when we have got a startup circuit on one side to help it start rather than provide a current source of its own. So these circuits can help you measure the temperature of the chip on which you are working. Now this is another place where analog people will survive. The temperature sensor on the chip, even though you have a digital chip, the temperature sensor will always be an analog device. Okay. Good. Right. Let's talk to the last particular sensoring modality which I am going to cover before I hand you over to my esteemed professors who will teach you for the next few days. And that is chemical sensors. Okay. Now, chemistry is a big department. Chemical engineering is a big department. They do 4 years of chemical engineering. And I have got roughly about an hour and a half to teach you everything about chemical engineering. Okay? We are good people. Of course, we can handle everything in an hour and a half. Now, there is a large number of chemicals. Now, till now, whatever we are measuring were physical quantities. We are measuring light. We measured heat. I did not do sound here, but I don't get time, but sound is another thing which we could measure. Okay? We measured force. We measured temperature. They were all physical quantities. They're kind of relatively nice things to measure because I know my electronic device, diode or transistor, is also dependent on the environment. So measuring the environment, my device is dependent on the environment, and I looked at which property of mine changes with the environment. Okay? By doing this, I was able to record these environmental changes. No sensor to stop water flow coming out of your mouth. Okay. I hope I haven't burnt the microphone. Now, it so happens the number of sensors are huge. Also, the way we measure them is huge, which is not unreasonable because, well, people have been measuring chemical sensors for a long period of time. People have tried to measure biochemical sensor. There's a glucose sensor in market. That's one of the first, the majorly successful sensor out there. Okay. There are electrochemical sensors. A chemical reaction happens and changes an electrical property, be it voltage, current, or resistance, or something else. There are calorimetric sensors. When a chemical reaction is taking place and it produces heat. The moment it produces heat, we can use all the thermal sensor analysis which we have done for measuring them. None of this is of interest to us because we're not going to study chemical engineering, right? That will be a very, very long lecture. The sheer number of materials which are there, it's of least interest to us. Don't get me wrong, people have tried to integrate different type of chemical sensors onto a silicon chip, but and this is also one of the visions for microelectronic circuitry. So till few years ago, we used to publish the International Silicon Technology Roadmap. And the roadmap, the leading scientists and industrial people used to come together and we used to figure out what can happen in future, what should happen in future. For a long time, what should happen in future meant what will be the processing power in 10 years' time, how much memory we will have in the SDRAM. that we have become kind of saturated. We have got, okay, we will say, okay, we will have more and more memory, more and more number of cores. How many cores do you have on your mobile phone? Octa-core, 8-core, 4 cores? I don't think anyone will have a single core system anymore. So this was the first prediction. So that was what we call as the Moore integration. Right? We are essentially just increasing the number of transistors on a chip. Now the story is that of more than Moore integration. Can we add things other than classical processing and memory? The first successful result was the camera. It was optical sensing. And now we are looking at 2 or 3 different types of things to go onto the chip. One is different type of sensors, other is energy. So we haven't been able to integrate battery on a chip till now. People have tried putting supercapacitors on the chip, but pure battery and energy source we have not been able to do. So people have tried putting chemical sensors. We will be looking at one particular type of sensing modality, which actually comes straight out of transistors operation themselves. And that is to use field effect transistor as a biochemical sensor. Okay? People have tried making what we call as chem FETs, various chemistry sensitive FETs. FETs by slight modification if they become gas selective or enzyme selective. The one which we are going to talk about are ion selective FETs. Now ions are interesting thing. They often happen in many chemical reactions. In this case we are only looking at pH for that matter. So let's do a quick MOSFET revision in case those of you who have been hearing too much about non-electronics for some time. So if you recall, the way we make a MOSFET is we have a source and a drain. We apply and we have a gate. Now below the gate there is generally just the P substrate. We apply a voltage on the gate. Essentially we give a charge to the gate, a positive charge. A positive charge attracts the negative charge from the substrate to come to the surface. Okay? Now the hatch line here, they are a dielectric. So negative charge cannot travel to the positive charge. It's like the Valentine's Day stopped by a professor, the dielectric being the professor, right? But because it's a negatively charged particles which have come near the surface, on two sides I have got semiconductor aspects which have got large number of electrons. So now I form a channel between source and drain, which can conduct electricity. So let's think a step back. What did we do? We applied charge on the gate, and that brought a channel to be formed. So it's all a story of charge. What happens in many chemical reactions? Ions move from one another, and we know ions are also charged, right? They carry charge. So the story then is, can we use the chemical reactions taking place to do the same kind of relationship, to form a channel or to put a certain charge there so that the threshold voltage changes here. Okay? So a typical SFET will look something like this. We just have removed the gate. Okay? So source and drain remains the same. You have a source, you have a drain, you have a p-type channel. You have still got the oxide. There is a thin dielectric oxide still there. Okay? On top of that, you allow liquid based chemical reactions to take place. Or if you are just measuring the pH, alkalinity or acidity of a material, you just mix it with that particular liquid. We do have a reference electrode which is far away from the transistor. We call that the reference gate, but it's not necessarily the gate of the transistor. Okay? So what we have done, we have taken the metal gate or the polysilicon gate away and replaced it with a liquid interface. We have a remote electrode, and to be very frank, rather than just having the silicon dioxide, we can also have other type of dielectrics there. Now, silicon dioxide surface has something very interesting. It contains a number of hydroxyl sites, OH bond sites, which are just there on the surface, which can either accept or donate protons. Protons are H plus particle, right? Hydrogen, so positively charged. And accepting and donating of protons, which means changing my charge. Okay. So, charge has a condition called charge neutrality condition. If we have a positive charge here and negative charge here, the charge will move till it becomes same. Same with liquid, right? You have got high pressure here, low pressure, it moves here to become the same pressure. So, what essentially happens, due to charge neutrality, we get a layer of liquid being formed on top of my dielectric. Okay? So, my dielectric is giving charge, and now we have got a separate layer of electric being formed. And that looks like I was having a capacitance, I was forming a capacitance here. Now, I have got a double layer capacitance which has been formed. On the bottom, I have got my TP type surface. On top, I have got charged ions which have come, very similar to what happens in a MOSFET gate. Equation wise, it looks as if it changes the threshold voltage of the transistor. Based on the number of charged particles the liquid has, that appears like the threshold voltage has been changed to these relationship. So, there is some, so there is a reference potential which has got a voltage. Then we have got a surface dipole potential of the solution. We also have the work function of metal contact, or in this case a poly contact, but most importantly is proportional to the ion concentration. Rest of these can be kind of solids. So, VTH MOS is the original threshold voltage of the MOSFET device, and then the ion concentration is changing my threshold voltage, how up or down it goes, and it is fairly linearly proportional to it. Now, the ion concentration follows the Nernst equation. It has got a relationship with KT, but it has also got a straight dependence on pH. You can see it is a kind of a linear function at the same temperature. Other than that, it works like a MOSFET. The only thing which happens here is the threshold voltage of the device changes based on the pH of the liquid in which it is, the liquid material it is. Now, we know in a MOSFET the drain current is dependent on the threshold voltage. The drain current of a MOSFET is beta divided by 2 VGS minus VT square. So, if something is changing VT, my drain current will change, and then that becomes a very simple sensor for me to measure. We also plotted the drain current versus the gate voltage. So, as a typical gate voltage, till you reach VT there is no gate voltage, right, and no drain current, and after that the drain current starts rising. This is gate voltage versus the drain current, not the drain voltage versus drain current. The classical MOSFET relationships go like this. We are looking at the gate voltage, and as you can see, based on the pH, the current shifts, the current changes. Okay. Except for that, rest of the relationship, if you also look at VDS versus IDS, so we are changing the threshold voltage, which means we are changing the VGS minus VT. Other than that, it looks kind of like a MOSFET. You have got a fairly MOSFET kind relationship except for this. Okay. Now, we did not make a my initial analysis when I explained to you, it was not the CMOS process, it was just we replaced the gate. Now, in a CMOS process, we have transistors, we also have many layers of metal. So, I am not going to be able to remove all the layer of metal and reach the gate directly. So, we can't make ISFETs as we just explained in a CMOS process. So, what is often done is you build the standard gate and then take the gate out as much as possible to different layers of metal. So, all of these are layers of metal. So, we have the standard gate and we just come out all the way till top and then put a dielectric on top of this. The passivation layer inherent in the CMOS process, which is generally a silicon nitride, that itself does the job. And then on top of that, this becomes a sensing area. Here is an SEM picture of how it looks like. You can see you have got the sources and the gates are coming all the way up, and on top I have got a passivation layer on which my things will take place. Okay. So, in a silicon CMOS process, we have got the passivation layer which provides the liquid interface. But now we know the passivation layer is not really the thinnest. It looks like a big capacitance which has come in place. It is not the classic ISFET. It looks something like this. So, I have got my transistor which has been formed here, which has got a gate capacitance. I am coming all the way till up to this top metal layer. On above top metal layer, I have put my silicon dioxide and silicon nitride. This looks like my passivation capacitance. And above that, I have all the solution part. So, remember earlier, I had the solution part immediately above my dielectric. So, the equivalent circuit now contains these capacitors in series with one another. So, what happens when I get capacitors in series? How does it divide a voltage? So, I apply a gate voltage here, a reference voltage here. What will I get here? There is also a capacitance here, the gate capacitance, right? So, I have got gate capacitance in series with passivation capacitance in series with the liquid capacitance. What voltage do I expect to see here? Can capacitors be used as potential dividers? Assume it is an AC voltage. So, if you look at from impedance point of view, if it is an AC signal from impedance point of view, it can act as. So, essentially what happens is the reference gate voltage which we selected as, remember the EG appeared in our equation for the reference gate voltage, that gets modulated by these, the passivation capacitance divided by the total capacitance. Right. Other than that, the equation still remains the same. It is the gate to source voltage, the drain to source current is the gate voltage if you keep source grounded minus the new threshold voltage which has happened. Okay. What is the total capacitance in this path? So, two capacitances in series, what is the total capacitance? Product divided by the sum, right? Much better way to remember that way, product by sum. Okay. So, my total capacitance has got the oxide capacitance as well as the diffusion capacitance, because I have got a gate oxide capacitance. Now, essentially what I am saying here, if this is C pass by CT, if my passivation capacitance is as close to total capacitance, this modulation will reduce. Okay. I do not want capacitance to reduce my signal, the parasitic capacitance to reduce my signal. So, things to make large passivation capacitance could be make large. What is the parallel plate capacitance? What is the formula for parallel plate capacitance? Epsilon area by D, where D is the gap. So, either I make the gap small, which means I make my passivation layer small, or I make my area bigger. or I use a better passivation material. I change the epsilon r, the relative permittivity. So, we will see the change of material in a while. There are some problems with pH sensors, and one of the biggest problem is, well, there are two big problems. One is temperature drift. So, if we go back to the previous slide, sorry, I should have talked about it then and there itself. So, look at the Nernst equation. I said my chi is a function of pH. It's also a function of temperature. Right? Yesterday when we were looking at sensor properties, we said a sensor should just measure what I'm trying to sense, not everything else. But because it's a function of temperature, it's going to be temperature dependent, including my pH measurement. So, if I am making ISFET as a pH sensor, I also need in parallel a temperature sensor to measure the absolute temperature to compensate for these effects. Okay? If I may move forward. The other issue which we often see is that they have drift. So, if you measure a pH now, you will get a signal. You measure a different pH after a while, you will get a different signal. And then you go back to measuring the same signal, there will be a jump, but it won't be the same jump. It will be different. So, for example, here you can see pH 6 has been measured here, then you measure 7, 8, you go back to 8. Yes, the signal has changed from 8 to 7, but it has changed differently. Now, one way you can see why it's happening, if you look at this signal, which is, if it were just 6, it would have constantly kept on going up and up, right? So, that is, even when I am changing pH, that slope profile remains the same. To some extent, it is because all the charges do not get removed. Some charges get trapped, so they keep on increasing the drain current. The other issue with these is a transistor. We checked, we have used transistors and diode as optical sensors. So, it is also photosensitive to, well, it is also sensitive to light. So, light and temperature effects also come in play here. So, some solutions to these problems require the top dielectric which we had. Initially, we use the classic passivation layer which is available in silicon process, that of silicon oxide and silicon nitride. A solution might be to use a better material than that. Ideally speaking, a high K dielectric would be nice. Of course, it comes with additional cost because passivation is given to you by free. Now, you have to remove the top layer and then deposit your new layer of oxide. So, typical oxide people have tried with our metal oxides, aluminum, tantalum or hafnium, and then they have used these as inherent pH sensors here. Now, if you look at the performance of ISFET responses versus various pH versus various oxide layers, if you can see things like tantalum oxide, it has a very good linear response. Silicon oxide, which is my native oxide, that does not have a very good linear response. It is a very non-linearly kind responses. And this is where your problem comes in. Do you want to spend more money to make a very good pH sensor, or do you want to spend, you are happy with silicon dioxide and happy with the non-linear response? Both approaches has been tried. One of the most successful pH sensor has been a DNA sequencing device, wherein they have used a chip to sequence the DNA completely, and there they have tried to go on with a different oxide rather than silicon dioxide. Now, till now we talked about a single ISFET, a single pH sensor. Ideally, we would like to measure pH sensor in an array, how things are happening in a square area or a rectangular area. Now, life again is not very difficult to what we did in image sensors world. We have got individual sensors. We create a 2D camera-like design for these individual sensors. Okay. And things people have done is DNA sequencing with these pH sensors, and it also shows promises in rapid vector measurement. Particularly during coronavirus times, it was quite hit because this could be something which should be used in the field without going through much of the testing. Now, pH is not the only thing which you can measure. Anything which can change charge can be used. So a number of other biochemicals have also been tried with SFET-like structures to measure these things. Few things before I let you go in peace. If I have 2D array, how do I read out my electrical signal from these pH sensors? So if that is my pH sensor here, a simple technique you can do is, okay, you know what, let's take an op-amp. Whatever is the voltage here will be the voltage applied here. Agree? That voltage comes here. I get a drain to source voltage. I have fixed my gate voltage. I have fixed my drain to source voltage. I have fixed my IDS. So all I'm going to do is measure my source voltage, and the source voltage then becomes my output. So that could be a very easy sensor to measure. So here we are now looking in the voltage mode concentration, and we're just looking at the source voltage rather than the current of this device. It's a bit noisy, more so your output is directly connected to your sensor. So the output variability could affect the sensor itself. You can do a current mode readout, and the current mode readout is not terribly different. Now you have got your SFET forming a current mirror with another transistor. The current mirror then gets copied, and then we copy on the other side, and we get I out as the current mirror. You can also do readouts very similar to the readout circuitry which we saw yesterday. What did we see yesterday? We had a diode, we had a reset device, and we had a source follower. Okay? We can have something similar. You have got your current producing SFET, you have got a reset device, you have a source follower, and you have got a row select switch. These are second stage amplifiers which are being seen. These are your current, the V bias. Remember, we applied an I bias current source. So we designed this circuit yesterday for a camera. We can use the same circuitry for a pH sensor as well. Remember, when I was talking about bolometers this morning, we could use a similar circuit in the bolometer operation as well. So the simplest amplifier, which is that of source follower, which is taught in first year, has got a huge range of application despite only having a unity gain. Single SFETs often are quite noisy. So people have tried double SFETs. So essentially what you do is you shield one of them. So it's shielded with a special layer. It's always producing the same output, but it's sitting next to your measuring SFET, and you take differential measurement. Okay. Application wise, these have been used to measure blood pH, particularly for looking at oxygenation and carbon dioxide concentration in blood, which is quite vital while we are doing in emergency departments. It was tried for SARS coronavirus too. Didn't work that well because we didn't have enough time to test it compared to the classical solutions. It has also been applied in monitoring environmental conditions, things like drinking water conditions, toxins, pesticides, measuring food quality, things like acidity of the food, nitrates, ions in the food. Applied in chemical industry to looks at paints, dyes. pH of soil is very vital for identifying if the crop, the quality of the crop which will grow. So soil measurement sensors have also been built with this, and so have saliva measurement sensors been built by these. Now in one slide, I have gone through a large range of chemical sensors. Remember, in the beginning I said chemical engineering is big. I won't be able to cover it. They said, okay, let's ignore everything. Let's just talk about a transistor-based sensor. Once I could measure pH of liquid, I can use that in a large range of application. Okay. In all of these applications, of course, the rest of the instrumentation will be slightly different, because whether you're looking at acidic or neutral and what are you doing with it, but the fundamental circuitry which goes in the building block will be very similar to the 3 circuitry blocks I have shown, either a voltage readout, a current readout, or a charge based readout from these devices. But just a point to note, ISFET based pH sensors are not the only way pH is measured. The good old standard was glass based pH sensing, and that is still used quite often. But this is becoming more and more predominant, particularly when you want an integrated single chip solution for measuring a large amount, measuring large characteristics of our system. Good. We covered chemical sensors. I said we'll take till 4 o'clock. We finish it in 3 o'clock, except one thing in chemistry, okay, which was measurement of gases. So we looked measurement in liquid. We did not look in gases. Okay. Now gases are interesting. We have been measuring gases for a long period of time, ever since we knew there were different type of gases in atmosphere. Ancient world in all cultures assumed air to be a single gas, right? This is why in all cultures you have the 5 fundamental elements: earth, water, fire. If you, some of them take Antariksh has a 5 final vital element, but from the days we figured out there is oxygen, nitrogen, carbon dioxide, we have been making gas sensors. Okay. Most of them based on chemistry of one type or the other. I will not be able to integrate all different type of chemical reagents on my chip, but I can see what else is happening to gases. So only 10 more slides and then Valentine's Day is all for you. Sir? For glucose levels, people mostly have gone with microelectromechanical sensor based systems, sir. And this is why you have use and throw kind of glucose sensors. They have become fairly standard. People have tried doing it with pH, but that has given much better responses. The other problem with biological system is that once something succeeds and gets the FDA approval, people don't want to try something newer things, but it's feasible. Now in gas sensing, we have 2 problems. One is to know if a gas is there or not, and this is for dangerous gases. There, just presence of these gases is enough to blow the horn and let everybody go out. Okay. The other problem is the amount of gases which are there. So for example, carbon dioxide, we are not worried about its presence in the room. We are worried when it becomes too high. Okay. Whereas things like ammonia, will be worried if it is there in the room, right? Or there are other dangerous gases which can kill us. You are not old enough to remember the Bhopal gas tragedy. If not, I'm sure you can read about it. It caused a major disaster in India. We did not have good, well, we had deployed some sensors, but then we didn't have this throughout the city. So there are many ways to look at gas sensing solutions. Some of them which have been successful in us applied the type of sensors which I have taught you till now. So I did teach you infrared sensors in the morning, right? And I told that some gases absorb infrared. So if you look at the absorption spectrum, a very good example is carbon dioxide absorbs 4.3 micrometer. Okay? So if we look at infrared spectrum around that thing, and the moment I see 4.3 micrometer being absent in my measurement, there is carbon dioxide or is there. Okay? So here what you will do is you will have an IR source and a sensor. Essentially, there's an air, you pass an IR source through it, have your IR sensor on the other side. Am I receiving 4.3 micrometer or not? If I'm not receiving, there's carbon dioxide in that sample. Okay? Unfortunately, this technique doesn't work with all gases, particularly with gases like hydrogen or oxygen. It doesn't do that well. Thanks. Now, this is where redox reactions come very handy. Things like carbon monoxide is often used by looking at redox reactions, and there you are trying to measure either voltage, current, or conductance of something. We'll just see a sensor in one way. Problem with gas sensors is if the gas sensors only measured one gas, like the carbon dioxide sensor which we just discussed, life would be nice. But redox reactions often react to many different type of gases at the same time. Many gases have oxygen in them, and that causes some issue. The other issue is most of these sensors have fairly short lifetime because they oxidize and then you can't do many things with it. Now, some examples of structures whose conductivity changes with presence of gases is things like zinc oxide, whose conductivity changes in presence of oxygen. So, essentially you can have a bar of zinc oxide, look at the current flowing through it, and higher the oxygen concentration, its conductivity will change. It also changes with hydrocarbons, things like methane. There lies the problem. Whether it's methane or oxygen, methane will kill me. Well, small amount of oxygen will not. A big amount of oxygen might do some harm to me. Okay. Similarly, tin oxide does ammonia, nitrous oxide, and several others. And some different deposition techniques also does ethane, methane, and propane. Okay. And then there is a big variety of oxides which people have tried with. There is molybdenum oxide which does ammonia and nitrous oxide, gallium oxide which does carbon monoxide and oxygen, wolfram oxide which does nitrous oxide. If you do it doped, you can also do nitrogen monoxide. Indium oxide does ozone. All of these are also temperature dependent. In most of these, the way we do, we want these oxides to undergo a redox reaction. The only way they react is if we heat them. So, heated oxide will react with the material there and then form something and change its conductivity. So, if you are just looking at a conductivity based sensor, we somehow need to heat these things. Now, you can think, what's the big thing about heating? Just take it outside in Warangal, everything gets heated up, including the professor's mind, right? How do we heat something on a chip? Sorry? One option could be increasing the temperature, but we are increasing the temperature of the entire room. Will not be interested, that will not be a great solution. We just want to heat these metal oxides which have been placed on top of the chip. So, how do you make a heater? Supply hot air possible? Air is not in my control. For hot air, I need to have something to heat the air first and then blow the air on top of my chip. Again, hair dryer is, what does the hair dryer do? It blows the air and then throws, right? So, I need another equipment. I don't want a multiple chip solution. Remember, right in the beginning, we wanted a single chip solution for everything. So, how do we make normal heaters? Have you guys seen a heater in your life? Or if you are living in Warangal, you would have never seen a heater. Do you have heaters in your place? Really? For which month? For once in a million year cold wave? What's the coldest Warangal gets ever? What's the coldest temperature in Warangal in December? How cold does it get in January? You guys never measure temperature. You guess, so yes, normal temperature, it's cold. Okay, I will trust you guys have seen an electrical heater. How is it made? There are 3 or 4 ways of making electrical heater, which are there in the market. The reason I'm going to asking you this question, I'm going to do the same thing on a chip. Okay? So you first tell me what kind of heaters have you seen. If nothing else, you would have got a water heater in your house. There are geysers and there is the old-fashioned water heater. So what do we do when we make heaters? Solenoid? What does the solenoid do? It's much simpler explanation than that. Sorry? So guys, you guys have, either some of you have become engineers, you are training to be engineers. The moment you see an electrical or electronic device, try to think what's in there. If not, open it. I'm sure these devices will stop working at some point in your life. That's when your screwdriver should come out. Before you throw it away, just open the damn thing. You're going to throw it away anyway, right? What's the harm in opening and having a look inside? As long as you don't connect it to power socket and then open it, unless you want to have an electric shock and become Superman or Superwoman, that should be fine. So, all last 8 days I have been saying things heat up when any conductor, when current flows through it, heats up. Agreed? What's the way to, till now we have been trying to avoid that heating. How to stop that heating? Let's try to increase that heating. So I can either increase my current, or what else can I do? Okay, go on. You're not wrong. The resistance. Something has to be done to the resistance. Yeah? Good. Good, good, good. So either we play with the resistance or we play with the current. I don't like playing with the current, because producing current requires energy and all those things. Well, energy anyway, I'm going to give a heating thing. So if I take a metal wire and pass current through it, it will heat up. Right? If I take a higher resistance metal wire, it will heat up even more. So if you remember the old water heaters, what were they? They were essentially two coils. I mean, they're still there in market in India, right? It's basically a loop of wire which there is a coil. There's absolutely nothing else. There's a circuit protector on top just to stop you from burning up. Other than that, it's just a coil. Right? I never understood why they charge money for making those things. It's a very simple electronic device. So we can make a chip heater by taking a metal and making a loop of it. We have metal in CMOS process, right? We have all those metals. If I purposefully make a loop and pass a current through it, it will heat up, right? And that's what we will do. Here is an example of a sensor like this. So you have got your a sensing film which has been deposited on top of this. So the yellow color is your sensing film. On top of that, we have got an interdigitated heater, and generally we use serpentine wires to increase the length. The longer the structure, the more hot it will give. So you may create a serpentine wire, deposit metal oxide of some type, and heat it. Now often we have to heat it at very, very high temperature. We are looking at 300 degrees Celsius. In the morning I asked you guys, what's the temperature range of commercial chip? None of them went 300 degrees Celsius. We're looking at 120 degrees Celsius or so. Because when you heat something, you need a place for heat to go away. Now on top I have got gases which I am reacting with. There's not much space for heat to go away. So people from Cambridge Sensors, they tried this approach wherein they removed all the silicon from below the heater. So we have got, you started with the silicon, build the heater, build the oxide, and then remove the silicon from below so that the heat could pass away. And this is their fairly successful thermal sensors which is there in the market. Okay? If you look at the number of heater design, now we are in the mechanical engineering domain. Right? Heaters can be designed in many ways. Which serpentine wire to go? Do we go single loop? Do we do double loop? Do we do square loops? Which side we fit? This is all mechanical engineering domain. Now we have wires. We generally draw wires. So yesterday when some of you were doing layouts, you drew straight wires. We like straight wires because, well, electrical engineers we don't know. But when you want to make a heater kind of structure, then you start playing with what should be the thickness, what should be the length, and then a large number of different approaches can come in. Typically, the reduction in resistance, as you say, we are looking at change in resistance when metal oxide react, is fairly linearly proportional to the concentration of the gas which you have. So if you have an air which is there, if you look at that, it's a fairly decent reduction. The problem, of course, you are heating the chip. Rest of my electronics doesn't like it. I do have other electronics on the same chip, right? It's not just I'm producing a volt conductance, I need another something else to measure the conductance. Now, a number of such sensors hence are made in specialized processes where the transistors have been trained to survive high temperature or have been designed to survive high temperature. Some of these processes are the ones which are used for automotive processes. A few days ago, we had a gentleman who had got a campus placement in Honeywell. So Honeywell used to have a foundry of silicon carbide, which is a high temperature foundry, and also for automotive and defense applications. So some of these processes have been used for making high temperature circuits. Good. Thanks. We did finish it much sooner than that, so you can actually go and buy your cauliflowers. Any questions till now? You can see my brain is dead today. I'm going much faster than I generally go. I go very slow explaining everything, but this is the Saint Valentine's curse on me for not being with my wife. Questions? You guys are all happy? So there are 4 sets of tutorials. Why don't we do some of these questions now? Okay? Let's do some questions now, so it will spend another half an hour, and then I will leave you in peace. So on the screen, you have got a relationship at different pH materials. This is the same circuit which you saw a minute ago. Okay? Now, which dielectric has the best response? What is Ta? Which element is it? Go on, somebody was saying something. Louder. Louder. I can't hear you. I've got big source of noise here. So you have to beat that noise. The signal has to be amplified. Look, I have got a headphone. I'm still shouting. That might be the reason why I'm having a headache, because I'm talking too loud. So did you say tantalum? So tantalum oxide is a very good thing. Why would we not use it? Sorry? Tantalum is available. I know, yes, some countries are trying to stop its flow from it, but it's not, it's costly also, that's true. The question is, why is it not preferable for a low cost sensor? It's not gold or silver. It's cost. So the main cost is not in depositing. Things like silicon dioxide are already there on a chip, right? You don't have to do anything else for silicon dioxide deposition. Whereas in order to deposit tantalum dioxide, you need to first remove the silicon dioxide and then deposit. So you are putting 3 or 4 new layers of production. Remember we did CMOS production the other day when each layer caused a lot of 6 sequence steps. So each extra step cost us a lot of money. More so because chip design process generally believes in using the same layer for everything, right? Be it some processor, memory, or these devices. Now if you're saying, okay, for the rest of them do it that way, for my 5 chips do it separately. So you could be a millionaire and then want to spend that amount of money, or else it becomes fairly costly. So what kind of effect are we seeing here? We just saw this effect. We call it drift. The sensor response is just changing with time. What it did not tell you, how do you reduce its impact? So think of a way to reduce the impact of this drift. The answers to all the tutorials questions are being provided to you online. So I'm not going to tell everything, but you should start thinking on this. Let's do question number 14. 13 we just talked, we need a heater and all those things. So I need a 4.3 micrometer IR detector for carbon dioxide. What detector should we use? How will we go about answering that question? We did it this morning. So 4.3 micrometer photon would have an energy. How do we calculate its energy? hc by lambda. Once we have found the energy, we need to find a semiconductor whose band gap will enable us to measure this, whose band gap is small enough, because it will have very small energy, right? So it should have a band gap is small enough to compensate for this. So you'll have about 60 questions to answer some of these questions which I have already taught you, and some of these questions which you will have to think on your own. Okay? Good. Let me see. If I have missed anything. Oh, sorry. Oops. So we did the mass sensor lumped parameter tutorial the other day, didn't we? I have provided extra questions for you to play with. One thing which I would like you guys to try is to write a MATLAB or Python code to simulate the behavior of resonant sensors. How will you go about doing this? Have you guys been taught how to solve ordinary differential equations in MATLAB or Python? The senior ones would have? Yes? Junior ones, no? How do you, have you been taught numerical approaches to solving differential equation? Newton-Raphson method has been taught to you? It's precisely the same. But the only difference being you don't have to write the code for Newton-Raphson method. Somebody would have already written that for you. So there are ODE solvers in MATLAB. ODE 45 is a good solver for simple problems. As the fourth order Runge-Kutta solver, the same solver is provided in Python. So essentially you just need to describe the system equation in formal Python norms and then simulate it. It will be a good idea if you can write the code. I was hoping to do it, the exercises here. If not, on some other day one of my colleagues might run it. But if not, try running it, and if it doesn't work, do send me a message and I will put a code online on the same shared drive so that you can run it on your script. What's the preferred language here, Python or MATLAB? I'm not going to write a code in C. Let's be honest, it's been too late. So these ODE solvers in Python, or the ones which MATLAB uses, are actually not written in C or Python. They are written in the mother of all scientific languages, which is Fortran. There are still people who code in Fortran. Good. So that will be one thing which will be worth trying to. And once you have done a single resonator, try to write the code for coupled resonators, and then you can see how the thing moves up and down. Remember we talked about two pendulums. Oh, we said we wanted to do a pendulum experiment, right? How do you make a pendulum experiment? I will figure out a way and leave for you guys to play it with it. Good. So you have 60 questions online to try. All the 60 questions have been answered for you as well, which would be a good revision of whatever I have taught you. Hopefully you have learned something while I have been here. If you have absolutely not learned, the room is good enough, cold enough to enjoy it. And at least you have tried your hands-on cadence. I wish you all the best. Good luck and bye for now.
But gone down to earth, okay, slow. So slow learners, how they, so basic level understanding explained clearly. Okay, thank you very much, sir. But actually expected were only experienced teachers as well as scholars is supposed to actually this course. Okay, PhD level as well as that experienced teachers. This level of course is conducted. But so luckily you are, so BTech student level he has start that course. Okay, right. Thank you very much, sir. It is my honor to invite our HOD and as well as my coordinator, Professor P. Snehadir also say two words, and maybe after that maybe the participants, maybe just one or two participants just maybe have. So your feedback also.
You have to connect your feedback from.
Yes.
Good evening, Professor Bhaskar and Mr. Anil Garu and Nidhar sir and my dear participants. So, you have been listening to Professor Bhaskar the past few days, and indeed I also, whenever there is a free time, then I also try to attend. And and indeed a lot of information, and it is just not animated. The question here is information passing is through animation. All the classes are very much animated, and then he made all the participants to involve directly, and it was totally a dialogue. It's not just a monologue. So, and the state of the art topic is. So hope all of you might have enjoyed, and then we will carry forward. And as the name implies, he is Bhaskar. So you have actually, I need not once again mention about what are his credentials, right? So he is the only student from NIT and REC Varangal indeed so far who had the feat of getting the Rhodes Scholarship, and till today that record is still not broken by anyone from REC or NIT Varangal. So, and subsequently, actually you can see that there are only very few who choose the teaching profession, who actually are passing out BTech from the REC or NIT Varangal, and he is the one who has chosen with passion the teaching, though he had ample opportunities to his end, but then that was his passion, and then really he is doing more than justice whatever the profession that he has chosen. And as the Bhaskar means the sun god, wherever, whichever country you go, right, the sun is there all the time. He just shines wherever it is, and then similarly Bhaskar, whether he is in India or Germany or whichever country where he has served, and then he had been shining and then making there is a sloka from who Lord Shankara has written on Lord Dakshinamurti. नानाचिद्रघटोदर स्थित महादीप प्रभाभास्वरं ज्ञानं यस्य तु चक्षुरादिकरणद्वारा बहिस्पन्दते जानामीति तमेव भान्तमनुभाति एतत् समस्तं जगत् तस्मै श्री गुरुमूर्तये नमः इदं श्री दक्षिणामूर्तये. So the lamp which is kept in a pot, how it disseminates all the light through the various perforations in the pot along the surroundings. Similarly, Bhaskar has been doing all his knowledge. He has been just disseminating to all possible means, wherever, whichever means. Though actually he need not take so much pains to travel all the way down and then just spend so much time leaving behind his family and spending so much time away is not required, but then it's passion. So the love towards is not only profession but also to see that the knowledge which he has acquired, that he wants to distribute it. So he wants to see that society should be benefited, and particularly the love towards alma mater, so that they actually brought him here and made him to spend some time living with the family behind. So therefore, we thank you very much, Professor Bhaskar, and we wish that you continue your relationship with your alma mater, and then hope we will continue to work in this direction. Indeed, I am also working in Law University, and the area is attached. We would like to see that what best we further do in the future. Thank you very much.
So request Professor Anjali sir and Srinidhi sir to join the state at Bhaskar.
Rather, we are honored to just know.
It doesn't look right, sir. So I have my electromagnetic fields, digital communication and microprocessor teacher standing next to me, which doesn't look right.
In fact, we feel proud to see our students in this position. Such a great honor it is to fill state our own student achieving greater heights. In fact, you all would have liked the way Professor Bhaskar delivers a lecture. Okay, it is something very different from what you heard earlier from many speakers. Okay, so that is one thing that we all want from any professor, like the students as well as the faculty. I mean, the most student-friendly way and the faculty-friendly way of disseminating knowledge is something that is a unique quality that I have seen in Professor Bhaskar, and that's what even the present-day students and faculty would like to. So I hope the tradition will continue, and then we'll be in touch with Professor Bhaskar for future, collaboration. And I also request Professor Bhaskar to initiate any continuous activity with the present research scholars or faculty, so that there can be an ongoing active collaboration going on between the Bhaskar Institute and then Professor Bhaskar Institute and NIT. Maybe I kindly see any such possibility of a continuous activity in terms of maybe giving a kind of a small opportunity for the research scholars and faculty here to participate in one of the research activities, whether it's funded or non-funded doesn't matter. But I think that active link should be there is what I think.
Thank you very much. We'll try my level best.
Yeah. Thank you. Thank you.
Thank you, sir. Sir.
Yeah, nice.
Thank
Yeah.
you. Sir, thank you very much, sir, for inviting me here, giving me an opportunity to come back.
So you'll be invited again and again. Yeah.
So please make a point whenever you are visiting India, please visit.
Okay, if there are any participants who want to say anything, just.
Now I will sit.
First of all, good evening, everybody. My name is Kiran Chand. I'm currently pursuing MTech in Robotics and AI in JNTU Sultanpur, Sangareddy. So, first of all, thank you very much, sir, your insightful lecture and guidance. Actually, this is totally electronics domain maximum. I'm from mechanical background. Actually, sir, first I came that I saw robotics, robotic head I saw, so it will be connected to my domain. I thought I came that. So I understood many things. The combination of many engineering domains will complete the one product. And so in between the sessions, I think second day or third day in the CIDR lab, I was demotivated, sir, because of electricals. I don't understand circuits totally. So personally, I told Bhaskar sir, so sir, I was demotivating. I said like that. Sir said, next slide, total mechanical. This whole class, you will be understanding. Nobody cannot understand. So sir said like that. Sir has motivated me, and sir not only taught in theoretical, he has given more practical knowledge also. Practical way how we can do things. Like you have given full of what effort make it practical, sir. And I have never seen like this type of lecturer, sir, because you are from so much big states, UK and Germany, but you are treating us very humble way, sir. That was very nice, sir. I was never expected like that way. It was new experience for me, sir, and my notions are breaked, sir, coming to here, and I learned not on theory, practical way also, sir. Many things. Thank you so much, sir, and thank you so much, Muralidhar, sir. Thank you so much.
Any other person? Scholars or MTech students? Anyone? Yeah. MTech students are there, no? Sitting, no? Continuously? PhD scholars? Okay, no problem. Right, okay, sir. Feeling shy, a little bit shy, but everyone want to speak, but the
Yes,
problem.
we call it an end, sir.
Huh?
We call it an end. You tell them about it.
Yeah. So BTech students are recently joined BTech students. Third year students, you want to speak?
What they are thinking is actually easy because robotic head, there are no, they are not.
Come, BTech students. So all 8 students should come, all 8. సో వీళ్ళకి ప్రీ రిజిస్ట్రేషన్ విత్ 8 మెంబర్స్ వచ్చారు కేఈ నుంచి. సో 10 మెంబర్స్ 10 స్టూడెంట్స్ థర్డ్ ఇయర్ స్టూడెంట్స్. సో దెన్ we have to.
First of all, good evening, everyone. Good evening, everyone. This is Yogita Rajuri from Kaktiya University. Actually, we don't know what's happening here. Up to coming here, we don't know. So, ma'am informed that there is a robotics class in NIT. So, you can go and visit and you can learn something. So, first of all, I'll thank Murlidhar sir. And I also thank Bhaskar sir. We learned a lot, sir. And thank you.